welcome to the ATAR Notes July lecture series. My name is Isabel and I will be taking you through preliminary chemistry, so year 11 chemistry. Hopefully I can teach you some things today, and yeah, I'm super excited to get started, so I'll just jump right in. As I said, preliminary chemistry today, and a little bit about me. So I'm Isabel, I'll be lecturing you today, I guess. And I graduated in 2022, so last year, and now I study a Bachelor of Applied Science, Exercise Physiology at the University of Sydney, which is super fun. I'm really enjoying it so far. In the HSC, I did 3-unit maths, English Advanced, Chemistry, Bio, and Modern History, and I ended up getting a Band 6 in all of them, which is super cool, and then I got a 99.3 ATAR. Some non-school related facts about me, not that you were wondering, but I like to dance, play touch, and I like going to the beach and doing water sports like surfing and stand-up paddleboarding. So if you look to the side there, the top image is one of me paddleboarding in Hamilton Island over the summer, which was super fun. And then the bottom one is of the quad at Sydney Uni. It's a very pretty building, a very old building. Lots of tourists are there. I don't have any classes in there, but I like to take photos of it while I walk to my actual classes because it's just a really pretty building. So that's about me. Another thing about me that isn't on this slide is that while I'm recording this, I am just a little bit sick. So if you see me struggling, just know it's because I'm a little bit sick. So if I sound funny and if I'm like taking quite a few water breaks, that's because I'm sick. But it's fine. It's all good. Yeah, just thought you should know that so you don't think I'm like weird or anything. Yeah, moving on. So the game plan for today is that we'll do a little intro, so some of my like general tips to year 11 chemistry, and then we'll do a crash course of all of module 3, so we'll go through the entire module 3, all the inquiry questions, all the dot points. We'll make sure that that's all solid, that you have all the info that there is to be had on module 3, and then what we'll do is we'll go to module 4 and we'll get a head start on some of the harder topics, or what I think are the harder topics, so enthalpy, entropy, Gibbs free energy, all that stuff. It's quite difficult to begin with, especially because it's terms that you haven't really heard of before and concepts that are quite new, and it can feel very overwhelming. So my goal for doing a little head start on module 4 is just to kind of make it a little less daunting so that when you go into learning it in class, it is much more comfortable for you and it doesn't send you into a spiral of panic like it did me back in year 11. So yeah, and then all throughout today we'll be doing practice questions, discussing common mistakes, and at the end I'll give you some of my exam preparation tips. For me, chemistry was not my best subject in year 11. I improved a lot between year 11 and 12 because I took some time to really understand where I was going wrong in chemistry and how best to fix it. And I'm going to give you those same tips because I want us all to do well in chemistry. So yeah, another thing is there's a live chat going on right next to the slides. Should be there somewhere. But live Isabel will be answering your questions as best as she can. I'll be trying to answer everything. If you have any question, there's no such thing as a silly question in chemistry because I know firsthand that chemistry is very confusing. It can be very difficult. So you don't need to feel silly about asking any questions. I probably asked those questions myself before. Just pop in anything you want to know in there or anything you need clarification on, and I will get back to you on the live chat. So hopefully that's working. But yeah, I'll just get us started then into the actual lecturing content. But before I do, just another quick side note is that my monitor is over here on my right, like here. So if I'm looking here throughout the lecture, it's because I'm looking at my monitor. Again, I don't want you to think I'm weird or anything by like looking over here. So yeah, just a heads up. Yeah, so I'll just get started. I'll start off with some advice, and I think it's very important to hear this. So the preliminary course, the Year 11 course for chemistry, is designed to form a very, 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 very important kind of foundation for your Year 12 studies. So some of the topics, especially in Module 3 and Module 4, they pop up again in the HSC syllabus. And if you don't have a strong understanding of the things in Module 3 and Module 4, it can be very difficult to keep up in Year 12 because it's all assumed knowledge. It's all stuff that you should have done. So it's very important that we get all of this very down pat and just that we're very confident in things, especially because Module 3 is all about reactions, and reactions is like the main thing in chemistry, I guess. So you want to be able to see a balanced chemical equation and know what type of reaction that is. And you can't do that if you don't have the very strong foundational knowledge of Year 11 chemistry. So I would highly recommend not ignoring this and not chucking it aside as soon as you're done with learning it, because it will come back to you later, I can assure you. The stuff that we'll cover from Module 4 today, that stuff also comes back up again in Year 12. So again, don't just ignore it when you learn it. It's there for a reason. And another thing I want to emphasize is that the best way to study chemistry and succeed in chemistry is to just do a ton of practice questions. So wherever you can find practice questions, do those practice questions, and those will really help you improve. If you're struggling, practice questions is the way to go. Just doing them constantly. That's how I improved in chemistry, and that's how a lot of my friends who did chemistry, who were struggling at the beginning, just getting familiar with all the different types of questions you could get, all the different reactions that you can get, that can really help in an exam. And yeah, another thing I'd like to point out before we get started is you'll notice that in the syllabus a lot of the dot points are conduct practical investigations or something like that, and those all refer to your experiments that you should have done in class. And I'd say it's a really good idea to know your experiments and know what the aim, the method, the results were, and understand what's happening behind all of that, because for me, at least, the experiments were a really good way of me learning the different types of reactions, seeing it happen, and seeing like the signs of these reactions and all of that. That helped me understand it much more than just seeing the reaction written on paper. So I think it's really valuable to like actually pay attention when you do the experiments, and they're actually quite fun. Some of my best memories in chemistry were doing a bunch of experiments, like doing combustion, doing precipitation reactions, all of that stuff. So yeah, pay attention when you actually do pracs. Actually, like, do the discussion questions that the teachers give you after pracs. They're really good at consolidating your knowledge. But yeah, I'll get started on Module 3. So Module 3 is reactive chemistry, and reactive chemistry is very cool. I like reactive chemistry. It's it's just cool. It's one of my favorite topics that I did in chemistry, just because it feels very like chemistry. It feels like what the movies say chemistry is, if you know what I mean. But if you don't, that's fine. So an important thing to remember when we talk about reactive chemistry is the difference between physical and chemical change. So here's just a comparison. So physical change is the form of the matter is altered, but the substance itself is not transformed into another. So for example, like changing states, so water going from liquid water to ice to water vapor, that's a physical change because it's not changing this actual substance into something that isn't water. It's just changing its form. So these are usually reversible, like changing states is reversible, and the intermolecular forces change. Then we have the chemical change process. So process in which substances are altered involving the rearrangement of the atoms. So this is, for example, going from an acid and a base to salt and water. The acid and base doesn't just change state to become a gaseous acid and a gaseous base. It changes into something completely different chemically. So it's a rearrangement of atoms. Some signs of chemical change, is that like a color change, odor, release of gas, those kinds of things are usually signs of chemical change. And in the terms of like writing a reaction, chemical change, a new substance is formed. Something that you didn't have before has been completely made. So that's that. When you talk about changes in physical or chemical changes, it's important to talk about the changes in force. So keep that in mind when you're talking about physical and chemical change and when you're thinking of reactions. So the first part of the syllabus is talking about different reaction types, I guess. And so the first reaction type that we have is a synthesis reaction. So it's called combination in the image on the right, but it's known as synthesis in the syllabus. So this is when we have one substance A, let's say, and then we have substance B, and they combine together to make one substance that is made up of like A and B. So if you look at the example, we have the Haber process, which is something you'll learn in year 12, and we start with nitrogen and hydrogen gas, and then what happens, it makes ammonia, and it still has that nitrogen and the hydrogen in it, but now it's rearranged into only one product, so two become one basically. The opposite end of the spectrum is decomposition reactions, where we have one product breaking down into one reactant breaking down into two products. Sorry there, not one product, one reactant breaking down into two products. So in synthesis, we have two reactants becoming one product. In decomposition, we have one reactant becoming two products. So if you look at the image, it does a good job of kind of showing you what's happening with like the little smiley face circles. But an example is this reaction where carbonic acid is changed into water and carbon dioxide. So yeah, you can tell what's kind of happening in the reaction by the names. So synthesis, you're making something. Decomposition, you're breaking something apart. So that can help you remember how many products and how many reactants there are. So that's the first type of reaction. It's very simple and it's very easy to identify. The next type of reaction we have is combustion. So combustion I always associate with fire, and burning. And basically this helps me remember that it's exothermic. We'll talk more about what exothermic and what endothermic means a little bit later in module 4. But exothermic basically means that it produces heat. So it's an exothermic reaction that involves the burning of fuel in oxygen. So the word equation that we use for it is fuel plus oxygen is carbon dioxide and water. So that's complete combustion. Complete combustion means that there's excess oxygen, there's enough for the fuel to completely combust. But sometimes in an environment where there is not enough oxygen, we have incomplete combustion occur. So this can form this is the reaction between fuel and oxygen again, but instead of forming carbon dioxide and water, it forms carbon monoxide, so CO, and soot, which is just carbon as a solid, and water. So sometimes incomplete combustion is just fuel plus oxygen is carbon monoxide and water. Sometimes it's fuel plus oxygen becomes soot and water. Sometimes it's fuel and oxygen becomes carbon monoxide, soot, and water. So it's different. It's different depending on the how much oxygen there is. So if you have very, very limited oxygen, you'd get just soot and water. if you have a little bit more oxygen, then you'll get carbon monoxide and water. And then if you have excess oxygen, you'll have carbon dioxide. So a good way to remember this is complete combustion is when there's excess oxygen. So that one in the products, it has the most oxygen molecules. So carbon dioxide has 2 oxygens, whereas carbon monoxide only has 1 oxygen. So that's incomplete versus complete. So that's just how I remembered my incomplete and complete combustion. There's lots of different ways to remember it, but that's just how I did it. So that's one reaction, and this is a very important reaction to remember because this comes up again in Year 12 and also in Module 4. So it's important to know this one. So the next one is another very important one because this comes up again in Year 12, and this is a precipitation reaction. So this is when the reaction between 2 aqueous solutions produce an insoluble solid, and this is called the precipitate. So if you look at the little image, the precipitate is that blue stuff at the bottom, and the equation, when you have the states in the equation, it should be 2 aqueous makes an aqueous and a solid. And a common question when it comes to precipitation is identifying what product will be the precipitate, which will be the solid. And to do that, you use your solubility rules. So solubility rules are very important, especially in Year 12, but in Year 11, at least for my school, we were given solubility rules when we needed them, but we weren't expected to remember it until we got into Year 12. So I'm not sure if that's what happens at every school, but I thought it's safest to just assume that we need to know solubility rules. It's always good to just know them because it will make it quicker. But yeah, so the best way to remember solubility rules, at least the best way for me to remember solubility rules, is the acronym NAGSAG. So these are all groups that are soluble. So the N is for nitrates, the A is for ammonia, G is for group 1, sulfates, acetates, and group 7. And then the little asterisks, if you look at the bottom, there are a couple of exceptions. So if sulfate is with calcium, strontium, or barium, it becomes insoluble. And if group 7 ions are with lead, magnesium, or silver, it also becomes insoluble. So yeah, it's something that you'll have to remember. Yeah, know your exceptions. So for sulfates, how my teacher explained it to us was the exceptions for sulfates are Castro-Bear, so Ca for calcium, Str for strontium, and Bear for barium. And then for group 7, the exceptions were PMS, so P for lead, PB, and for magnesium, Mg, and S is for silver, which is Ag. So that's that. Moving on. Basically, the only way to do precipitation is with your solubility rules. So that's something worth getting to know and getting familiar with. If you can get familiar with it now, it will take less time for you to memorize them when you get into Year 12. So just a thought. And acid reactions. So again, acid-base reactions and acid reactions are very important in Year 12. You do a whole topic on acid bases and their reactions. So it's very worth paying attention here. So basically, you have 3 main acid reactions that you're expected to know in Module 3, and the first one is acid-base, also known as neutralization. So what happens is you have an acid, you can usually tell it's an acid because there is an H at the front, and then you have a base, and you can usually tell it's a base because there is an OH at the end. And these combine to form a salt and water. If we look at the example, hydrochloric acid and sodium hydroxide form sodium chloride and water. And then that's acid, base, and salt and water. So yeah, pretty self-explanatory there. The next reaction is acid carbonate reaction. Again, another important one because this also comes back in year 12. But for this, what happens is you have an acid and you have a carbonate, so it's a metal carbonate usually, and this forms a salt, and it forms carbon dioxide and it forms water. So the example is a reaction between hydrochloric acid and magnesium carbonate, and yeah, it's just balanced out there. But an important thing to note is when you perform this type of reaction, since carbon dioxide is being formed, what you'll notice is there will be bubbles coming out of the solution. So whenever you see bubbles, that means that there's a gas being produced, and it's just a matter of being able to tell what gas is being produced. So you'll notice in the acid metal reaction, you have an acid and a metal causes salt and hydrogen gas to be formed. So there's an example with hydrochloric acid and magnesium. So if you had these reactions and you were asked to determine whether it was an acid carbonate or an acid metal, just based on the fact that there were bubbles produced, something that you can do is collect the gas and test which gas was produced. So there are different tests to figure out what gas is being produced. For hydrogen gas, it's the pop test, so stick a flame in and there should be a popping sound, and for carbon dioxide, you've got the lime water test, so it turns milky if there's carbon dioxide. So that's a way to differentiate them if you ever need to. So those are the acid reactions, and so yeah, this is a practice question that I think is very good. So the question is, which of the following correctly identifies the gas or gases produced when hydrochloric acid is reacted with zinc, sodium hydroxide, sodium carbonate, and sodium hydrogen carbonate, respectively? So, if we go from the first reaction, which is hydrochloric acid with zinc, that's an acid-metal reaction, so we know that it forms hydrogen gas. So that leaves B or D as our answer. So we'll keep narrowing it down between those two. The next reaction is a base. So sodium hydroxide has that hydroxide, which usually indicates a base, and it's with an acid, so that forms a salt and water. Now, neither of those are gases, so no gas is produced, so B and D are both still in the running. So sodium carbonate, we have a sodium carbonate, so a metal carbonate and an acid reacting. So when that happens, we know that that forms a salt, carbon dioxide, and water. Now, carbon dioxide is produced, so again, B and D are both still in the running, meaning that we just have to really figure out what the reaction between an acid and sodium hydrogen carbonate is. So, in this situation, you have an acid, which is hydrochloric acid, and sodium hydrogen carbonate. It is a really good idea to write down what the equation is. So what you'll find is it's hydrogen chloride, so HCl, plus NaHCO3, which is sodium hydrogen carbonate. And what that makes is NaCl, so sodium chloride. And then what you have left over, so that's your salt, and then what elements or pieces that you have left over is you have that H from the hydrochloric acid, and then you have the HCO3 from the hydrogen carbonate part of sodium hydrogen carbonate. So what it will form is water and carbon dioxide. So you're not forming any hydrogen gas in this reaction, so therefore you're just forming carbon dioxide. So D will be your correct answer here. So yeah, that should be your process in this kind of question, just narrowing it down, going through all the reactions, and then figuring out which option is right. So D is the correct answer in this case. Yeah, so moving on. That was the first inquiry question all done, which was very quick. Yeah, basically for the first inquiry question, it's really just knowing those reactions. Like that's really all you really have to do for it, and all you really have to know. So know those reactions, and you're all set for the first inquiry question. Then we have the second inquiry question, which is, I think, the toughest one in Module 3. So we'll go through this one in quite a bit of detail, but this is all about predicting the reactions of metals. So we'll talk about the reactions of metals in water, dilute acid, which we've kind of already talked about, and oxygen and other metal ions in solution. We'll talk about some patterns in metal activity on the periodic table, which correlate with ionization energy, atomic radius, and electronegativity, which are all concepts that you should have covered in one of the earlier modules. And then we'll look at redox. So redox is quite difficult. It may take some time to understand, so we'll take some time on that one. But yeah, we'll just get started right into the second inquiry question. So first, looking at the reactivity of metals with water, well, yeah, basically metals that are more reactive will have a faster rate of reaction, so you'll see a more aggressive reaction typically with more reactive metals. For example, sodium in water, it reacts quite violently and quite aggressively, so you have to look away quickly or else it will burn your eyes. On the other hand, if you put lead in water, nothing happens. So that's just an important thing to note, that reaction rate is very different depending on what metal you're putting in the water. And in general, what happens is water plus metals creates hydroxide salts. So for example, if we're putting magnesium in water, we'll create magnesium hydroxide and also hydrogen gas. So some things to note about water reacting with metals is that some react with liquid water, some react with steam, others don't react with liquid water but do react with steam. So some react with both. It's all it depends on the metal. So that's that. And also another thing is that a decrease in the temperature of the water increases reactivity of some metals, including potassium, sodium, lithium, barium, calcium, and there are also some metals that don't react in water at all, so they do not form a hydroxide salt and a hydrogen gas, and this includes lead and copper and gold. So just some things to think about. If we look at yeah, we'll look at that next anyway. I don't know why I was getting ahead of myself. Yep, so moving on, we have metals with acids. So we know that when acids react with metals, it produces salt and hydrogen gas. We talked about that before. Some differences between more reactive metals and less reactive metals is that more reactive metals would produce lots more bubbles, which indicate the hydrogen gas, than the metals that are only a little bit reactive. Those will have less bubbles and smaller bubbles. So potassium and sodium react quite vigorously, so lots of bubbles, and the hydrogen gas can easily ignite. So like I talked about before, there's the pop test that can determine that it's hydrogen gas, and that's because hydrogen gas is flammable. So yeah, lots of hydrogen gas can ignite. Then magnesium and calcium react with dilute acid with less bubbling. Zinc, aluminium, tin, and iron have very slow bubbling, and then some have no reaction at all. So that's that really. I don't know really how to explain this without just saying you kind of have to just remember these reactions. So you have to remember that a water and metal is a hydroxide, a metal hydroxide. Oh, sorry, a metal hydroxide and hydrogen gas, and then you just have to know that in this case it's a salt and a hydrogen gas being produced. So yeah, just keep this in mind. Know that if it's more reactive, lots of bubbles, less reactive, smaller bubbles. And when we look at the trends in the periodic table and how it can help us determine metal reactivity, it'll be much easier to figure out whether something has slow bubbling or whether it's bubbling a lot. So that's something to look forward to later on in this lecture. But yes, so when we talk about reactivity of metals with oxygen, metals and oxygen form a metal oxide. Who would have guessed? But basically how this metals and oxygen can be determined by experiments where it's heated in the presence of air or plunged into a glass container with oxygen. So some trends in the periodic table, that magnesium, aluminium, zinc, and iron, they burn readily and form oxides. A thing to consider is that iron oxide is rust. So that's just something interesting, I guess. So iron oxide can be the rust that you find, and that means that without oxygen, rust can't be formed. So if you put rust, like a nail, an iron nail, in a vacuum sealed container, theoretically you can't have rust being formed. But that's not the point of this. So yeah, lithium, sodium, potassium, calcium, and barium, they also burn readily and they form peroxides. So an example is sodium peroxide there. And then you have some that react slowly to form oxide layers known as rust. I just talked about rust just then. Iron oxide is also a type of rust. Yeah, you're not really burning anything to form a rust, so it occurs much slower. And yeah, it's just like the outer layer. Then we have silver, platinum, and gold, which has no reaction at all. And an interesting thing that my teacher pointed out to us when we were learning this is, if you think about silver, platinum, and gold, they're all metals that are used very often in jewelry. And if we look back at the other side, you'll also see that gold, platinum, and silver have no reaction with acid, and it also has no reaction with water. So you have gold over there and platinum. It's important to think about why those were chosen for making jewelry, and it's because that jewelry is always in contact with oxygen, and if you're washing your hands with like rings on or a bracelet on, you might get water on it. You don't want it to be violently reacting, or else that would be really bad. So the reason they chose those metals for jewelry is because they don't react. They don't react to acid, oxygen, water. They can just be. So that's something to keep in mind, something interesting, and just a little nugget of general knowledge. So yeah. So another thing is the reaction of metals with other metal ions. So it can be determined by observing if the metal in the solution displaces the solid metal, so a metal displacement reaction. The more reactive metal goes into solution generally. So an example is if we put copper solution with magnesium solid, what will happen is you'll see a deposit being made around the magnesium strip that was originally in there, and that's copper solid, and then the magnesium is going into solution. It's becoming aqueous. So we'll talk more about metal displacement reactions when we talk about redox. But first, what we'll talk about is trends in the periodic table. So just to recall and recap, the trends in the periodic table from the previous modules, we have atomic radii, the radius of the atom. Pretty self-explanatory what that is, but the trend is that it increases down a group. So if you look at the little diagram at the bottom there, you'll see that the radius gets bigger down a group, and then across a group, the radius gets smaller, so it decreases across a period. Not a group, sorry, a period. And then first, ionization energy. So just recall that ionization energy is how much energy is needed to remove the first valence electron in a gaseous state. So that increases across a period and it decreases down a group. And the same trend is shown in electronegativity. So just again, another recall is that electronegativity is how likely it is to attract an electron to form a bond. So this also increases across a period and decreases across a group. How this ties together with the reactivity of metals is that as ionization energy increases, reactivity of metals decrease. As atomic radii increases, the reactivity of metals increase. As electronegativity increases, reactivity of metals decrease. So, putting it in more in better context, if we looked back here, we'll see that ionization energy increases across a period and down a group. So as ionization increases, so it's increasing so ionization energy increases across a period. So ionization energy increases across a period. That means that across a period, the reactivity of metals decreases. And the more to the right you go, the less reactive the metals become. And yeah, so if you just follow the trends of ionization energy, atomic radii, and electronegativity, you'll be able to figure out the patterns in the periodic table of where the most reactive metals are. So in general, if we look at the periodic table down here, I know it's quite small, but the more reactive metals are up here in this corner here, and it becomes less reactive the more you spread out diagonally this way. So that's a general rule of thumb. That's something you can keep in mind when thinking about what bubbles more, what bubbles less, all of that stuff, what has a more vigorous reaction, what has a slow reaction, what has no reaction. So we see that gold and silver are on the far right side of the metals, and same with lead, which we also saw before was not very reactive in water. So if you remember some of those key ones that don't react and the key ones that do react, so we remember that sodium is very reactive in water, and that lead is not very reactive in water. We can kind of guess the kind of spectrum and where it's more reactive, where it's less reactive, if you know what I mean. So yeah. So that's that. Here's a kind of a summary of the reactivity of metals. So we have the most reactive up there, going to the least reactive down at the bottom. I won't read out the whole list, but another thing is if you look at the reduction potentials on your data sheet, it follows a similar list. So if you look at that, we'll talk about that data sheet when we talk about redox, but yeah, if you're ever stuck in an exam and you don't know your reactivity series of metals, if you look at that data sheet and you look at the potentials, it's going from most reactive to least reactive, top to bottom, generally. So yeah. So we're going to look at redox reactions now, which is a little bit tricky, so we'll spend some time doing them, but basically, redox reactions are a type of reaction that involves the transfer of electrons. So there are two parts of a redox reaction, oxidation and reduction. And the way we remember what each one is oil rig. So oil is oxidation, is loss of electrons, and then rig is reduction, is gain of electrons. So basically, when you have a redox reaction, one compound is getting oxidized and the other compound is getting reduced. And some terminology that you have to be familiar with is the oxidizing agent, or the oxidant is the species that causes the other one to be oxidized. So it does not itself get oxidized, it's reduced. So it's quite confusing, but the oxidant or oxidizing agent is reduced, but it causes the other to be oxidized. So it's just best to remember that it's opposite. So an oxidizing agent or oxidant is reduced, and then a reducing agent is oxidize. So it's a little bit confusing, but like all things in chemistry, it starts out confusing, but the more you practice it, the better you get at it and the less confusing it becomes. So for redox reactions, the first thing to remember is oil rig, oxidation is loss, and reduction is gain. And the way that we are able to determine whether a loss or a gain is happening is when we look at oxidation states, which we'll talk about in a bit. So if we look at this net ionic reaction here, we can see if it's redox or not. So let's look at it. So we have, this is an example of the metal displacement reaction we talked about a couple slides back, but we start off with aqueous copper, and then we have magnesium solid, and then this reacts to form magnesium aqueous. Ooh, sorry if that sounded weird. My earphone just like fell out. Anyway, so we have magnesium aqueous then, and copper solid. So is this redox? Let's see. So we have copper as an aqueous. We'll look at one at a time. So when we're looking at a reaction and determining if it's redox or not, best way to do it is look at one species. So we're looking at copper and then determining what happens to its electrons there. And then we look at the other one and see if the opposite is happening to its electrons. So if copper was gaining electrons, that means the magnesium has to be losing electrons. That kind of thing, we have to figure that out. So the questions we ask ourselves are, is there a transfer of electrons happening? And then we can figure out which is oxidized and which is being reduced. So if we look at copper, copper starts by being like an ion that is 2+. So it's 2+, that's fine. It's a little bit positive. Then what happens is when we come on to the other end of the reaction, copper has gone to being just a solid, being not an ion, not charged, it's neutral. So we've gone from positive to neutral. How does that happen? That means we needed a negative to counteract that positive. So that means that copper was gaining electrons to become that solid copper. So the aqueous copper was gaining electrons to counteract that positive charge to become the neutral solid copper. So that means it's a gain, which means it's part of the rig, oil rig, it's reduced. So copper is reduced. If we look at magnesium, we start with a neutral solid, so it starts just as magnesium, and then it becomes an ion, it becomes positively charged. How does that happen? We needed to add a positive, and how you add positives is basically you're taking away negatives. So basically it's losing electrons, and without those electrons it can't balance out the positive, which makes it positively charged here. So that means that magnesium is losing electrons, which means it's part of oil. Oxidation is loss, so it's oxidized, so magnesium is oxidized. So all of that I just said can be summed up into these half equations here. So if you just look at those, you'll see that copper plus 2 electrons, so that's a gain, that's reduction, it becomes copper solid. Then magnesium is oxidized, so it loses 2 electrons. So together it's a redox reaction. Something a little bit more complex that goes down in the redox kind of syllabus is that it can occur in an acidic solution, and this requires a few more steps than just adding electrons to either side of those half equations. So how you go about these is you have 4 main steps. First, you balance all the elements aside from hydrogen and oxygen, so you ignore those to begin with. And then what you need to do is to balance that oxygen, you add water, so H2O, you add water to the other side of that oxygen. And then to balance the hydrogens that you added from the water, you just add hydrogen ions to the other side, and then you balance the charges. So what this looks like is if we're looking at acidified permanganate to solid manganese oxide, sorry, my words got a little jumbled there, but if we're going to acidified permanganate to solid manganese dioxide, we first write out this equation. So it goes from the acidified permanganate to the manganese dioxide. Then we need to balance the atoms that aren't hydrogen and aren't oxygen. So this is basically already done. And then what you need to do is you need to add water to help balance oxygen. So as you can see in that little equation there, we've added water, and this is just one oxygen to begin with, but then since we put a 2 in front of the H2O, that means it's 2, so it becomes the 4 on the other side. It's just all balancing equations. That's another thing about redox. It's very important that you're confident in balancing equations, because there's quite a lot of balancing of equations here. But yeah, you just follow the steps that I mentioned before. So we added the water to help balance the oxygen, and now that we have the oxygen all balanced, now we just have to balance the hydrogen. So the 2 H2s means it's 4 hydrogens that we need to add to the other side, and then we need to balance the charges by adding electrons. So you have 2 neutrals on the other side, and we need to make sure that it's 2. It's also a neutral on the left side. So on the right side, since you have the solid and the liquid, those both don't have any charges. Charges is 0. But on the right side, we have that 1 negative from the acidified permanganate, and then we have the 4 positives from that hydrogen ion. So that means that overall we need 3 electrons to balance it out, and there you go. So it's a lot of just balancing equations, really. But just remember those 4 steps. First, balance other atoms other than hydrogen and oxygen. Add your water to balance oxygen. Add hydrogen ions to balance the hydrogen, and then add your E's to balance the charge. All of that balancing can get you that final redox equation. Sorry, just fixing my little earbud there. So as I talked about before, the standard potentials on your data sheet in chemistry, it can help you understand the reactivity series of metals. So it kind of follows the same pattern, but also it shows us the strongest oxidant and weakest oxidant, strongest reductant and weakest reductant. So basically, going from top to bottom, it becomes a stronger oxidant. So it becomes more likely to lose electrons. And then from top to bottom, it becomes a weaker reductant. So it is more, it's less likely to gain electrons the further down you go. And how this ties in with your reactivity series of metals is that your more reactive metals are therefore more likely to want to reduce. They're more likely to reduce and less likely to oxidize. So yeah, that's basically that. We'll talk about using these standard potentials in a practice question in a second, but just remember the oxidant is the oxidizing agent, and this is more likely to let me start that over again. Oxidizing agent causes the others to oxidize. It does not itself oxidize, it is itself reduced. So keep that in mind when looking at this. Okay? Cool. So, oxidation states is another thing that's in the syllabus, and it's a little bit weird, but basically oxidation state represents the number of electrons that an atom can gain, lose, or share when chemically bonding. And if there's an increase in an oxidation number, that means that an oxidation reaction has occurred, because that increase in oxidation number means a decrease in electrons, which means you're losing electrons, which means oxidation. Then A decrease in oxidation number means a reduction reaction occurs, because that decrease in oxidation number means that it has become more negative, which means that more electrons have been added on, which means it's gained electrons. According to oil rig, gain means reduction, therefore a reduction reaction has occurred. So here are some of the rules about oxidation states. So the first one is that the oxidation state of elements on their own is 0. For example, zinc as a solid, sodium as a solid, it's all 0. And it's the same for elements in molecule form. So for example, oxygen and hydrogen, that's O2 and H2, their oxidation states will also be 0. And the oxidation state of an atom as an ion is the same as the charge of an ion. So the oxidation state of zinc ion is 2, and the oxidation state of a chloride ion would be -1. So yeah, that's pretty self-explanatory. I just think of oxidation states as like the exact same as the charges, basically. That's the easiest way to remember it. If it's ever different, they'll let you know. But another thing is that the sum of oxidation states in a neutral compound is always 0. So yeah, just simple maths can help you work that out. And then also the oxidation state of oxygen is generally 2 negative. So yeah, it's 2 negative. 2 minus. That's something that you might need to use in a redox reaction, but there's not much I can say about it other than that's what it is. And yeah, oxidation state of hydrogen is usually +1, and oxidation of fluorine is usually -1. So those are the general rules for oxidation states. You'll just need to remember them. The more that you look at redox questions, the more that you'll remember these rules, really. So we'll just move on. Yeah. Oh, okay. There we go. So if we look at this question, so oxidation states, let's look at this practice question. Which is the oxidizing agent and which is the reducing agent in the following reaction? So if we look at this, if you remember from the rules, H2 has an oxidation state of 0. So that's 0. And yeah, O2, we know O2, 2, 0. Yeah, so I'll just okay, I'll just explain this with my words then. So we start with a 0, and then basically what happens in H2O, that H is the H is a +1 oxidation state. There's 2, so it's +2. So the H goes from the H side, it goes from 0 to +2. That means it's lost electrons. That means it's been oxidized. If it loses electrons, it's oxidized, which means that hydrogen is the reducing agent. Because if you remember from my little spiel earlier on, the oxidizing agent is not oxidized, it's reduced. So the reducing agent is not reduced, it's oxidized. So if H is going from neutral to +2 in oxidation state, that means, what does that mean? That means that it's going neutral to +2, which is more positive, which is a loss of electrons, which means it's oxidation. So if H is being oxidized, if hydrogen is being oxidized, that means it's the reducing agent. Okay? Then we have oxygen. So if we look at oxygen, in that form, it's 0. The oxidation state is 0 because that's how it is as a molecule. And it becomes -2 in that gaseous water there. So it goes from 0 to -2. It's more negative. The oxidation number has decreased between the reactants and the products, which means that electrons have been gained. So since electrons have been gained, according to oil rig, it's been reduced. So reduction is gain. So oxygen has been reduced, which means that oxygen is the oxidizing agent, because oxidizing agents get reduced. So you see how it is a little bit confusing? Like, even I'm tripping over my words here because I'm saying like reducing and oxidizing so much, and it's so easy to get confused. So it's very, very important that you solidly understand what oxidizing is, which is loss, what reducing is, which is gain, and then what oxidizing agents and reducing agents are, which is completely separate to oxidation and reduction. It's the opposite way around. So it's a lot. I know it's a lot, but it's something that has to be done. But yeah, that's basically how you go about working out your oxidizing and reducing agents based on your oxidation states. So yay, we can move on. So a common thing that comes up in the syllabus and in questions regarding redox is the galvanic cell. So these are devices which utilize chemical energy released by redox reactions to generate electrical energy. And here are the key parts of a galvanic cell. We have the electrode, where the metals are placed within solution. We have the anode, where it's the negative electrode, and the cathode, which is a positive electrode. So how you remember that anode is negative and the cathode is positive is it's the same as anion and cation. So cations are positive ions, so the cathode is a positive electrode, and then the anions are negative ions, so anode is the negative electrode. The anode is where oxidation occurs, and again, I find some fun ways to remember what happens where, because it can be quite confusing. So how I remember it is oxidation is loss, and loss is negative. You don't want to lose something, that's bad. So it's at the negative electrode, and then the cathode is positive, reduction gains it, gains electrons, it gains something, something is added, that's a plus. So reduction occurs at the cathode. Another key thing that's a part of the galvanic cell is the salt bridge. So the salt bridge is filter paper soaked in a salt solution. Most of the time it's potassium nitrate. That's because potassium nitrate just does a really good job of what the salt bridge is supposed to do, which is something we'll talk about in a second. But yeah, so those are the key parts. Then we also have the electrolyte, which is a substance in aqueous or molten state that conducts the electricity. So yeah, that's that. And all of this is set up with that voltmeter, and the electrons flow from anode to cathode. How I remember it goes that direction is we go from A to C. A is before C, so we go from anode to cathode, and goes through the voltmeter, and that generates electrical energy, that movement of electrons. So we'll go into more detail about this. As I said before, electrons always flow from anode to cathode, and basically at the anode, oxidation is occurring. So as oxidation occurs, it's losing electrons, and those electrons are then free to move through the voltmeter and into the other side of the galvanic cell, where it can be gained by whatever is being reduced. So yeah, that's what it looks like. If we look at the example here, we have zinc and copper. So if we look at our little reaction situation, our reduction potentials, we'll see that copper is more reactive than zinc. Since copper is more reactive than zinc, what's going to happen is that that copper is going to be reduced, and when it's being reduced, it's gaining electrons, and it will form a deposit over the electrode. And then in the zinc side, it's just in solution, and it's moving those electrons across. So yeah. The salt bridge is very important. It basically is just a house of ions. So you have, it's usually potassium nitrate, so it's just potassium and nitrate ions. And these ions are able to move and can therefore stabilize the charge in each of the half cells. So the half cells is obviously like the zinc half versus the copper half. But the cations in the bridge move towards the cathode and the anions move towards the anode, and this prevents the cathode from accumulating negative charge. So the cations are positive and they move towards the cathode to prevent it from becoming too negative. And then the anions, which are negative, they move towards the anode and prevent it from becoming positively charged. So that's the salt bridge. It plays a very important role. You can't do the galvanic cell without the salt bridge. So that's something important to remember. So now we'll talk about cell potentials in these galvanic cells. So how you go about these kinds of questions are firstly to determine the half equations and then use the table of standard reduction potentials that is on your data formula sheet. You look at there, look and find those half equations that you determined were a part of the galvanic cell. And then what you do is you calculate the total cell potential by adding those together. It's important to note that on the data sheet, they're reduction potentials, not oxidation potentials. So what you'll be needing to do is for the oxidation half reaction, you'll need to change that that potential into the opposite sign, basically. So we'll go through an example so you can see what I mean. But yeah, we'll do that. So a practice question is, a strip of magnesium metal is placed in an aqueous 1 molar solution of copper sulfate solution. Will a spontaneous redox reaction occur? So what we need to do is we need to find out what that potential of the redox reaction is, and we do that with the half equations. So first thing that you need to do is find out the half equations. So wrote those out here. Magnesium becomes magnesium aqueous and 2 electrons, and then reduction, copper plus 2 electrons becomes copper solid. Then what you do is you look on your data sheet, and what you'll see is that we have magnesium, which is the normal one. We use the opposite of, sorry, let me rephrase that. Sorry, that was really badly worded. Okay, so on the data sheet, basically the copper is being, is the reduction. Copper is being reduced. So you're using that normal potential. Then magnesium, it was originally a negative, but since we're flipping the equation around, it's become a positive. So then what you need to do is just add it together, and then what happens is you have 2.7. Since it's positive, that means that it is going to be spontaneous. So I should have led with that, but if the potential of the redox reaction is positive, that means it is going to occur spontaneously. So at the end, you should always write a concluding statement, especially since the question was like a worded question. Like in maths, if it's a worded question, it's best to give a worded statement at the end, not just numbers. Same thing with chemistry, you should always have a little concluding statement to make it very clear that you think that it will be positive at the end. You think that it will be spontaneous because it's positive. So add that in where you can. And yeah. So another practice question that we have here is this one. And this one is pretty fun. Yeah, the question is just what is the order reactivity of the metals based on the results. So we have a student perform the following test to investigate the relative activity of metals. In each test, the metal strip was placed in solution containing ions of a different metal. The results are shown in the diagrams below. So if we take a look at each individual diagram, we'll be able to see these are metal displacement reactions. That's something good to point out. at the beginning of doing your question. Just know that it's a metal displacement reaction, and that can help you think about how you're going to proceed with the question. So first we have metal X and metal Y, and metal Y is being deposited on metal X. So what that means is that metal Y is less reactive than metal X, because metal X wants to go into solution and metal Y is becoming a solid. So that means that metal X is more reactive than metal Y. So that means it can't be C. Can't be C, and it can't be D. So that leaves A or B. Then if we look at the second test tube, what happened, or beaker, or whatever this is occurring in, we see that metal Z and metal Y, we have metal Y being deposited on metal Z. That means that metal Z is more reactive than metal Y. So that means that, well, that means that metal Z is more reactive than metal Y, and if we look at the last one, we'll see that's congruent, because metal Z is no reaction occurring, no displacement occurring, it's just staying as an aqueous solution, which means that Z is more reactive than X. So that means Z is our most reactive metal. That's B or C. We already ruled out C, so it must be B as our answer. So as I talked through that, you could kind of see the thought process. You just go through each of the test tubes. Like I did with that question on what gases will be produced, you go through each column, you go through each reaction until you narrow it down to the one multiple choice question that is correct. If this wasn't multiple choice and you had to write an answer, you're working, you would have to write reactions for the metal displacement reactions and then justify. But in this case, it's just multiple choice, so you can just use the process of elimination. That's always my take with multiple choice. I love using the process of elimination because it's just easier, in my opinion, than just trying to find the one correct answer. Just eliminating the wrong ones goes a long way, especially in chemistry. So yeah, that's a good practice question. Another one I have is this one. So an electrochemical cell is represented below. So this is a galvanic cell of sorts. And you want to write the relevant half equations and the balanced net ionic equation for the overall cell, and then calculate the standard potential. So going through this bit by bit, first we have the relevant half equations. So what we see for the iron is it is becoming more positive, which means that it is being oxidized. So that means that we have start off with iron 2+, and then that becomes Fe3+ and an electron. And then we use the same thought process, do the same thing with our bromine over there. And then with all this information, we can write the net ionic equation, which is down there. And when we have that, all that information, we can use our standard potentials from our data sheet. And then I've calculated it there for you. There's your answer. I should have made it so that it comes up one at a time, but I'll just talk you through the standard potential again. So basically, what's happening is the iron is being oxidized, so it's losing that electron. Since it's losing that electron, the potential for iron was flipped around, so it became a negative. So that 0.77 became a negative, and yeah, instead of being positive, because we want the oxidizing potential, not the reducing potential, if that makes sense. But yeah, that's how you approach the question. The most important part is getting those half equations right and that balanced net ionic equation right. The standard cell potential, it's just all about using that data sheet, and you really have to get those half equations right if you want to get that data sheet part right. So focus on the first part of the question, the relevant half half equations 1, because that is more important. So if we look at the setup for this cell, the galvanic cell that was in the question, it would look a little bit like this. So we have our iron that's being oxidized at our anode, and then the flow of electrons is moving through towards our cathode, which is where the bromine is. So if you're ever asked to draw up something like a galvanic cell, this is what you want it to look like. You use your standard drawing methodology. You use your normal, use your ruler. That's a very important thing. My school is quite strict on the whole you should be using a ruler for straight lines thing. So when you're drawing a beaker, everything is done with a ruler except for those curved edges at the bottom. Everything else in this should also be done with a ruler. But yeah, if you're ever asked to draw something, this is a really good basic one, and then you just change the labels. So this is what your galvanic cell looks like if you have to draw it for an exam. So yeah, that is all of the second inquiry question done. I know it was a lot. We spent quite a bit of time on it, and I get that it's really confusing, so if you're still confused, hopefully you've been asking me questions and I've been answering it for you. But yeah, so now we'll move on to rates of reaction. This is much easier, so it should be much quicker to go through. But yeah, let's just get into it, I guess. So collision theory. Collision theory is something that's very important. It underpins all chemical reactions, and basically it states that a successful reaction is dependent on 3 conditions. First is the actual collision. So the reactant particles need to actually collide for a reaction to take place. Then the next thing is activation energy. So once they collide, they need to collide with a certain amount of energy. So there's a threshold. If it does not meet that threshold, then the reaction won't proceed. It will just collide and nothing will happen. It has to have enough energy, and all that energy will help break bonds and rearrange them and all that stuff. So activation energy is very important. And that's an important term because it comes back to us in our next module, in module 4. So keep that in mind. And molecular orientation. So the reactant should be arranged a certain way, and they must collide at the right angle. So if it collides at the wrong angle, it won't react properly. It needs to be in a certain way. So it's very specific stuff. So how does temperature affect reaction rate? Basically, temperature is the average measure. Oh, that was bad English. So temperature is the average measure of kinetic energy of particles within a system. And as temperature increases, the rate of reaction increases. So higher temperatures causes these particles to undergo more collisions because it's got more kinetic energy. It's vibrating more, moving around more. That energy means that there is more collisions, and it also means they have more energy, so it's more likely that they're reaching that activation energy threshold. So therefore, the likelihood of successful collisions increase, and yeah, so that's why reaction rate increases with temperature. Next is surface area. So when surface area increases, there's a greater area for reactants to react. So this means that more collisions can occur and therefore increases the rate of reaction. So if you look at the difference in the amount of surface area in A versus B, you can see that at B, you'll definitely have more successful collision. There's more ways that it can collide versus A. And a really easy way to increase surface area is by just crushing solids. Separating solids into smaller parts. It's just a really easy way of doing it. Next is concentration. So concentration is the increasing amount of particles per unit of volume. So increasing concentration, increased amount of particles per unit of volume. And basically with higher concentration of reactants, you just have more reactants, which means there are more particles that are able to collide, therefore increasing the chance of collision. So that's pretty basic, pretty self-explanatory. If you have less particles, they're going to be less likely to collide because there's just less of them. If there's more, just more likely to collide. So that's why concentration increases the likelihood of successful collisions. Then we have a catalyst. So catalysts, they aren't used up in the reaction. They come out the end being unused. But what they do is they increase the rate of reaction. So what happens is they provide an alternate pathway which has a lower activation energy. It doesn't actually lower the activation energy of the reaction, it just provides a different route to get to a lower activation energy. And yeah, basically with a lower activation energy, this means that more particles would have enough energy to successfully react when they collide, and this means that you increase the rate of reaction. So there you go. Pressure is related to concentration. So concentration was the amount of particles per unit of volume. Basically, pressure is just like gas concentration. So when you increase pressure and you decrease volume, so keep in mind that the relationship between pressure and volume is an inverse relationship. So as pressure increases, volume decreases, so on. So when you increase pressure, the particles are close together and the concentration essentially increases, which increases the likelihood of successful collisions. When you decrease pressure and increase the volume, the particles are more spaced apart, and this decreases concentration and decreases the likelihood of successful collisions. So that was the end of Module 3 and the recap. Hopefully you got a little bit from that. If you didn't, hopefully I've been answering your questions in the live chat. But that's it for Module 3. An important module, one that you should definitely pay attention to because a lot of it comes back around. And if you don't know it, it'll just get harder to know it later because you're spending so much time learning the other new stuff in Year 12 that it's hard to find time to go back and just consolidate your understanding. So try to understand it now. I know redox is really hard. I found it really difficult, if you couldn't tell by me constantly stumbling over my words, but it takes some getting used to. So don't stress, do more practice questions and you'll be good to go. But as for now, we're going to get a head start on Module 4, which is drivers of reactions, and we will get started on two specific topics. We're going to be getting started on calorimetry and Gibbs free energy and spontaneity. So these are definitely some of the harder topics in the Year 11 syllabus, just because it's got some things that you've probably never heard of before and formulas that you've never heard of before, and just it's very overwhelming to begin with. So again, as I said in the beginning, the purpose of this kind of head start is just to get you comfortable with Module 4, because Module 4 is very uncomfortable to begin with, and it'll make so much more sense in class if you have a bit of understanding beforehand. So that's the goal. So calorimetry, as I said before, I would talk about endo and exothermic reactions. So endothermic reactions is when heat is absorbed during the reaction. So the energy of the reactants is lower than the energy of the product. So basically, energy is absorbed, and delta H is positive. Delta H, you'll see it everywhere. It's just like, I think of it as like heat, change in heat. Yeah, so the delta means a change in something, so delta H is change in heat. And then we have exothermic reactions, which is when heat is released. So when we look at like the energy of the reactants versus the energy of the products, energy of the reactants is higher because some of that energy ends up being released, so the energy of the products is lower. So that's that. And because of all of this, the delta H is negative. So whenever you see a negative delta H, that's exothermic. A positive delta H, that's endothermic. Lots of reactions that occur are actually exothermic. Endothermic reactions are not rare, but you come across them less often. Exothermic is much more common, especially in the context of the HSC. A lot of the reactions that you see and do, they will be exothermic. An example is combustion, which we talked about earlier today. That's an exothermic reaction that releases heat. So yeah, this is the diagram. These diagrams are very popular in exams. People like to ask their students to explain what's going on in these diagrams. So I'll give a quick little explanation. So delta H in exothermic reactions are negative, and that's because heat is being released and energy is being released. So we start off with reactants, and they have like a certain amount of energy. Then once they react, they obviously lose some of that in the form of heat. Therefore, the products have a lower amount of energy. So that's why the products ends up being lower. On the other side, we have endothermic reactions where delta H is positive, which means heat is absorbed and energy is absorbed. So in the reactants, we start with however much energy we have, and then throughout the course of the reaction, forming the products, we have product with a higher amount of energy than the reactants because it's absorbed some of the heat. So in terms of like physical science of exothermic and endothermic reactions, exothermic reactions, you'll often feel like heat. You'll feel that like the beaker is getting warm or the test tube is getting warm. That's an exothermic reaction. If it's getting cooler, that's an endothermic reaction. So this is a very common question that you'll get. So this is like heat capacity. Q equals MCAT, which is that equation up there. You'll see it everywhere. So Q is quantity of heat, M is mass of substance being heated, C is specific heat capacity, which we'll talk about in a sec, and delta T, is change in temperature. And this is in Kelvin, but really change in temperature in Kelvin and degrees Celsius ends up being the exact same, because it's just how the conversions work. So So specific heat capacity is the amount of heat energy required to increase 1 gram of a substance by 1 degree Celsius. So increase the temperature by 1 degree Celsius of 1 gram of a substance. So most of the time it'll be given to you, unless it's water, where it's also given to you on your data sheet. So for water it's 4.18 joules per Kelvin per gram. And you have to be very careful with your units in this kind of situation, because if the mass is in kilograms, make sure you convert it into grams before using the specific heat capacity. So basically this formula is the cornerstone of all calorimetry that you do. As I said before, the units are very important. Take note of the units, specifically when mass and heat capacity. But yeah, so that's just the formula. We'll look at an example of where you would use this formula, which is heat of combustion. So this tells us how much energy is released when you burn 1 mole of a chemical compound in a combustion reaction. So the steps that you would take to do these, first is you find the change in temperature. And once you do that, it's always given, like it will give you the starting temperature and the finishing temperature. You just work it out by simple subtraction. Then the next thing you do is you use that formula that we used before. Again, make sure that your units match up, because that is a very common mistake. Very common. The reason I keep emphasizing it is just because of how common that mistake is. Like, I've made that mistake before. I'm sure most of my friends have made that mistake before. It's very common. So just trying to drill it into you now so you don't make the same mistakes that I made. But yeah, so heat of combustion, we have that formula that we use, Q equals MCAT. What we need to do first is figure out what the different parts of that MCAT is before finding out the Q. So that includes the number of moles, and then you also need to that includes the number of moles for the um, for the for the fuel being burnt. I don't know why I just had like a brain breakdown just then. Anyway, you need to calculate the number of moles of fuel being burnt, and then you can then calculate the heat of combustion. So we'll look through a practice question. An experiment was conducted to determine the heat of combustion of ethanol. The following data was obtained. We have the initial temp, final temp, change of mass of the spirit burner, and mass of the water. And calculate the theoretical heat of combustion for ethanol. And then it gives us the formula of ethanol, because we'll need that formula to figure out the moles of ethanol that was burnt in that spirit burner. So, the process can take a while. First step was to find out the change in temperature, and that delta T is 55 minus 25, which is 30 degrees Celsius. Then the heat capacity formula. This is so important, but the Q equals MCAT. Q equals MCAT. The M is the mass of the water, not of the ethanol. Okay, it's the water. It's always the water, or in heat of combustion questions, it's always the water. It's not going to be the ethanol. The ethanol, they give you that mass because that's to find out the moles, and that's for a later step. It's the mass of the water. That's why it's in red. It's really important. It's the mass of the water. It's very confusing, but it's the mass of the water. So it's that 102, and then you multiply by 4.18, which is the specific heat capacity of water. That's why we use the mass of water. And then the delta T, and then we get it in joules. So then what we need to do is, what we want to find out with heat of combustion is how many kilojoules per mole is being released. So how we get to that is we need to find out the number of moles, and this is where we use the mass of ethanol. So use the math, again, another bad speaking moment. So we use the mass of ethanol here, and then the molar mass that we calculated from the formula that they gave us, and then we find it's 0.022 moles. Then what we need to do is, since we want it in kilojoules per mole, we need to change that joules into a kilojoules, and then divide it by the number of moles, and then we get our heat of combustion. So then, again, we have to have that little concluding statement at the end to let them know that we're wrapping it up, let them know that we actually have a final answer. If you're under stress in an exam, it's really easy to have very messy working, and it can be difficult for markers to find your answer, and they might not be able to see it, so that might be a reason that you don't get the marks that you actually deserve. So that's why that concluding statement becomes really important, because you want to make it easy for the markers to see your thought process and see your answer. And they'll be so happy that they can easily get to the answer on your page, that they'll easily give you the marks. They won't think twice about it. So it's important that we get that concluding statement in, just because it makes the markers' life easier, and that makes the markers happy, and it will mean that for the rest of the paper, they like you and they'll be nice to you. So that's a little trick. Make the markers on your side. I had quite a few messy papers in high school, and when my papers were messy, you couldn't see where my answer was unless I wrote that concluding statement at the end. I could have lost so many more marks if I didn't have that concluding statement, because the marker couldn't find the answer amongst my scribbles. So that's just a little piece of advice, a piece of advice for anyone who under exams just starts being the messiest person alive. Write that concluding statement. It can do you a favor. It can get you some marks that you might have lost if you hadn't written it. So that was the thinking process for that question. Heat of combustion, it can be broken down into two main steps. First is the Q equals MCAT, and then second is delta H equals Q on N being the number of moles. So delta H, I just use for heat of combustion, just H, and that equals kilojoules over moles, so it's Q over N. But Q being in kilojoules, not joules. So that's why I said keep in mind the units, because a very easy place to go wrong is keeping it in joules, but then at the end using the units kilojoules per mole, because that's what you're used to giving as a unit for heat of combustion. So keep that in mind. Convert your joules straight away into kilojoules, because it'll just make life easier. But yeah. So now we'll move on to Gibbs free energy and spontaneity. So this is a little bit tricky, so we'll take it slow. Okay, so part of Gibbs free, oh, again, sorry for the bad talking this whole time. But yeah, Gibbs free energy, it's an equation that's made up of enthalpy, entropy, and also temperature. So we'll get to that equation in a second, but first, what is enthalpy and what is entropy? So enthalpy is H, so that's your delta H. It measures the internal energy of a thermodynamic system under constant pressure. So enthalpy is your change in, it's the same delta H as you've been using for heat of combustion and like exothermic and endothermic reactions. It's the same delta H. So that you're kind of familiar with, but the word enthalpy kind of makes it sound more confusing than it is. But that's enthalpy. And then you have entropy. It's easy to get them mixed up because they kind of sound the same, but they're completely different. So entropy is denoted by S. So change in entropy is delta S. And this is the level of disorder in a thermodynamic system. Now, this is a little bit difficult to explain, but it's all about randomness and how chaotic the arrangement of something is. So if we have a gas versus a solid of and some type of ionic compound, as a gas, it is much more disorganized because the particles are everywhere. It's in a bigger space, they're bouncing around. That is so much more disorganized than like an ionic lattice. So entropy would be greater in that disorganized gaseous state than it is in that ionic lattice. So it's a measure of the randomness, the disorder. So typically if something starts off as one reactant. So in your decomposition reactions, if you start off with one reactant and you end up with 3 products, that means that as the reaction progresses, you are increasing the entropy because it's becoming more disordered and more chaotic because you have those 3 products versus the one reactant. So it's a little bit tricky to wrap your head around, but if you overthink it, it just gets confusing. So just know enthalpy, internal energy, entropy, disorder, and that's all you need to know about the concepts. This is uni level kind of chemistry concepts, so don't read too much into it, don't think too hard about it, because you will get confused, because I got confused thinking too much about it. So yeah, just try your best. But basically how you use this stuff is here. So this is the Gibbs free energy equation. So delta G, which is Gibbs free energy, equals delta H minus the temperature times by delta S. So delta G is change in Gibbs free energy, and that's the unit. Then you have change in enthalpy, and you have change in entropy, and then temperature. And it's very important to note that that temperature is K. It is in Kelvin, it is not in Celsius. Since it's not delta T like it was in our Q equals MCAT, you can't just use Celsius and it will be the same as Kelvin. This is Kelvin. So if you don't know how to convert Celsius to Kelvin, it's plus 273, I believe. So I'll just fact check that for you because yeah, so 273, yeah. It's you add 273 to your Celsius, and that'll be your Kelvin. And yeah, so that's the equation. And basically, spontaneous reactions occur without external energy added. So that's what spontaneity means. It means we don't have to do anything, the reactions just happen by themselves. And it favors the formation of products just under the conditions where it's supposed to happen. So if we look at delta G, we have when it's positive, it's not spontaneous. So unlike with the cell potentials, where if it was positive, it was spontaneous, this is the opposite. So when Gibbs free energy is greater than 0, it's not spontaneous. When it's less than 0, when it's negative, it is spontaneous. Another kind of side note about Gibbs free energy is that when it equals 0, it is an indicator of a reversible reaction. So there's that. So here's a practice question for Gibbs free energy and spontaneity. So the question is, for the Haber process, delta S equals minus 200, delta H is minus 2 times 45.92 at 25 degrees Celsius. And then calculate the Gibbs free energy, blah, 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 classify the reaction as spontaneous or non-spontaneous. So, for part A, what you need to do is just use the Gibbs free energy formula. How you do that is you basically just sub in the values, but don't forget that you need to add that 273 to the 25 degrees Celsius to put it into Kelvin, so it's the correct units. Once you sub everything in, you should get negative 32.2 kilojoules. Because it's negative, that means that it's less than 0, obviously. So delta G is less than 0, meaning that it is a spontaneous reaction. So part B is classify the reaction as spontaneous or non-spontaneous. So here, what you would do is you would write that concluding statement that says, therefore the reaction will occur spontaneously, or something simple like that, or therefore the Haber process occurs spontaneously at this temperature. Something along those lines to let them know that you've answered the question and you're done. So that's basically all that you need to do for Gibbs free energy. It's all just using that formula and calculating that formula. Sometimes there'll be extra bits and pieces you might need to do. You might need to calculate delta H using your delta H equals Q on N, and then Q equals MCAT. Those formulas, you might have to use that, and then use your delta H to be a part of the Gibbs free energy formula. But most of the time, you're just subbing in values, and the way that they want to trick you is with the units. So it might be in weird units. Yeah, that's basically, yeah, it will just be in weird units. So in this case, in part A, with the entropy, delta S, we had to convert it into kilojoules because it's in joules, and we want it in kilojoules to go with the delta H, which is in kilojoules. So to do that, they multiplied it by 10 to the minus 3, and then that'll put it into kilojoules for you, and then they subbed it in. So pay attention to the units, because that's where they're going to trick you. If you don't pay attention to the units, then if the number is weird, like you can tell when a number isn't exactly right. If it's way too big or way too small, it's a sign that you probably messed up the unit. So always check your units, and always put your units in your like concluding statement or last line, just to let them know that you actually know what you're measuring and you're not just throwing numbers around. So that's that. Some recap of all of that is here in this table. So if we have this equation, which is the Gibbs free energy equation, we have delta G equals delta H minus the temperature multiplied by delta S. So if we look at this, we can kind of figure out what happens at different temperatures and different degrees of disorder. So if we have a very low delta H and we have a very high delta S, we can see that because of the maths. How it will work out is that, if you have a low delta H and a high positive delta S, then how the maths will work out is that it will be delta G as a negative. It will always be negative, because if delta H is negative and delta S is positive, just if you do the maths, it'll turn out that delta G is always less than 0. So it will be spontaneous for all t. On the opposite side, if delta H is greater than 0, so if it's an endothermic reaction, and delta S is less than 0, so it's more organized than disordered, then it won't be spontaneous at all t. So if that delta H is much bigger than that delta S, and that delta S is negative, then the negative times the negative will cancel out. It will be positive. It will be non-spontaneous for all t. And then in the yellow sections of the slides, it will depend on whether it's a high temperature or a low temperature. So when it's delta H being positive and delta S is positive, it'll be spontaneous at high temperatures. Then when delta S is negative and delta H is negative, it'll be spontaneous at low temperatures. So these are all some ways that you can remember and figure out whether something will be spontaneous or not. But then again, you can just plug in the actual numbers into delta G and you'll be able to figure out whether or not it's spontaneous or if it's non-spontaneous. So that is it for the content. That's module 4. The tricky parts finished. The rest of module 4 is pretty chill. So that'll be up to everyone else to teach you. I'm done with the lecturing content, but I do have some tips and tricks, some final little bits of exam tips and that kind of stuff that I think you should know if you're doing chemistry, because chemistry is hard. So this is advice from me, who was someone who almost dropped chemistry after year 11. So chemistry is hard. That's why I almost gave up, but I didn't give up, and I ended up getting a band 6. So you shouldn't give up either. Basically, the understanding why you're doing the steps, so what's behind each of the steps, and the theory behind it, it can help you problem solve when you get to a tricky question. So if you're just memorizing like what you need to do to get to an answer, it's much less, you don't understand it, you're just memorizing the steps. It's much better if you understand what those steps actually mean, so that way if there's a change in the wording of the question, or they want you to figure out something backwards, like you'll be able to figure it out. You won't get stumped. So it's important to understand the why behind things and why they happen in chemistry. Another thing is with your calculations, get comfortable with them. So the main calculations that you have to do that we went through today is with redox stuff. It's not really calculations, but you do have numbers when you're balancing those half equations. So get really good at balancing equations, because balancing equations is very important. It can make or break your question. If your equation isn't balanced properly, you're probably going to do the question wrong. Or if they're super nice markers, they'll give you like a correct for previous error mark, but it won't be completely right. You can't get full marks on a question when you don't have the question balanced out properly. So get comfortable with balancing equations and your calculations. So in module 4, you have your Gibbs free energy calculations, and you also have your heat of combustion calculations. So your formula is Q equals MCAT, and then delta H equals Q and N. Those formulas, know them really well and know when it's time to whip them out, so that you don't have to spend time thinking, oh, what am I supposed to do for this question? The only way to really build that skill is just by doing a lot of practice questions and getting used to seeing a bunch of different questions and being able to go, oh, this is when I need this formula, this is when I need that formula. But in general, just get comfortable with those calculations, especially when it comes to moles, because moles is, there's lots of mole stuff in year 12, lots of stuff to do with ratios. Like when you get to titrations, moles becomes very important. So it's good in year 11 to get used to correctly calculating moles and being able to use them like confidently. But yeah, then the best way to study is to do practice questions. My school is really good at giving us practice chemistry questions. They gave us a lot of material to help us study, so that was really good, especially when it came around to our yearly exam. So just do whatever questions you can get your hands on, because that way you'll be able to improve. And the only way to improve is by doing practice questions, because you're not writing notes when you're in an exam. You're applying what you have written in your notes. And the only way to practice applying that is by doing practice questions. Then some common mistakes. So we went through a couple of the common mistakes before, but the main ones are messing up your moles, messing up your units, or messing up your simple maths. So with moles, it just comes with practice. Just make sure that you use the correct mass and the correct molar mass. Like when you're doing heat of combustion, it's the mass of it's the mass of the fuel, and then the molar mass of the fuel that you're using. You're not using the mass of the water and then the molar mass of the fuel. It's make sure it lines up. And then with the units, like we just had with that Gibbs free energy question, the units were a bit weird. One was in joules, one was in kilojoules. Make sure they're the same before you go subbing them in, just because once you sub them in, it's very easy to forget units, especially if you're not writing them down next to the actual numbers that you're subbing in. So put in your units, make sure they're correct, and the rest should be good. And then simple maths. So double negatives can really trip people up. So a negative times a negative is a positive. That's just something to remember. When you're doing Gibbs free energy, especially, don't go making, like, if delta S is negative, it'll end up being like a positive number on the end. Yep. What was I up to? Yep, so messing up simple maths, be careful of your negatives. Then when in doubt, you should use your logic to get out. Panic in exams can really mess you up, and it can stop you from seeing how easy it is to get the answer. So it sounds a little bit like, oh, duh, of course use your logic, but no. In an exam, if you see a tricky question, don't let exam panic cloud your thinking. I'll go over this in my next slide anyway, but just don't let panic get the best of you, because the answer is either on the page with multiple choice, or it's in your head somewhere. Like, they wouldn't assess you on something that you weren't taught. And then, yeah, don't give up on chemistry, because you might be like me. You might do really bad in year 11, but then get a band 6 in year 12. And you won't know until you keep doing chemistry until year 12. So, yeah. Okay, next slide. How to approach tricky questions. So, this goes with my logic kind of thought process, but basically you need to always write a balanced chemical equation for the question. This can also help you get a few extra marks for trying, because sometimes just writing that balanced equation can win you marks. So try that. But in the best case, writing that balanced chemical equation can help prompt you to realize what you need to do next and help you figure out what your next steps are. So when you get those tricky questions, what you need to do is first ask yourself these questions. So what do you know? If you're being told delta H, delta S, and the temperature, you can safely assume that it's a Gibbs free energy question. If you're given the mass of water and a temperature change, you can assume that it's heat of combustion, and then you just use your specific heat capacity in your data sheet to help you find the answer. So just write down what you know, and that can help you figure out what to do next. Another thing that's good to look at if you're having trouble is finding out what you need to know. So if the answer you're trying to figure out, if the question is calculate the mass of something, write that down. If you need to calculate the mass, most likely that means you need to get it from the moles. If you need to get it from the moles of what? What's the molar mass of whatever you're trying to find the mass of? Just figure out what you need to know, and then you can always work backwards. Another thing that you can do is figure out what module it's from. So if it's from module 3, it will most likely be a redox question or something about some type of reaction or rate of reaction. So if you see the word reaction, reaction is like the key word in module 3. So if you see the word reaction and or like rate of reaction, it's probably module 3. So once you know that, you can kind of figure out what topics are in module 3, what skills did I learn from module 3, and then you can figure out what to do. Another thing to do is looking at the balance equation, see if it can tell you anything. So this applies specifically to when you do redox stuff. When you have that balance equation, and with the harder ones, when we did it in like the acidified permanganate example, when you have that, it can be quite tricky to figure out how to charge balance it at the end. That's where a lot of people struggle, because they've balanced the actual elements, the H, the O, the permanganate stuff, the manganese, all of that. They've balanced that, but they don't know how to balance the charge. So then, again, what you just need to do is like visualize it and then write down write down the E's on each side, because when you're adding the E's to the question, it looks like a letter E, right? So what you need to do is just like write down on each side, count. So if it's positive ones, then write like +4, plus like actually write stuff down. It's okay to scribble on your paper. It's okay to have a very messy working out, as long as at the end you put it all back together with a nice concluding little sentence. Because if you don't have that, then your scribbles are just nonsense and the teachers get upset. So like scribbling on your paper is fine. Annotating the question or the equation is fine, as long as it's readable and as long as your answer is clearly laid out somewhere on the page, you should be all good. So yeah, the balance equation can tell you a lot. It can tell you ratios, it can tell you how things connect. So just pay attention to that balance equation, because it has some secrets. It will tell you something eventually if you look hard enough into it. And here, some final advice about year 11 and like general study tips. Firstly, it's year 11, it's not year 12, so it's not the scary one yet. It's not the worst high school year yet. Well, year 12 is not the worst year, but it's not the most stressful year of high school yet. So don't overstress it. It's all good. Any mistakes you make in year 11 are mistakes that you can learn from and then not make in year 12. So if you want to think positively about everything, every mistake that you make in year 11 is one less mistake that you'll make in year 12. And the less mistakes you make in year 12, the better you do. So like, don't worry about it. It's much less scary than you think. Another thing is to work together. The HSC is a team effort, and a mistake that my school made was that they did not tell us that it was a team effort. They did not tell us that you could get so much from working with other students instead of competing with them. So I didn't really get to the whole like working in a group thing until year 12. So if you start in year 11, that's really good. A good study technique that I used quite a lot, not just for chemistry, but for other subjects as well, was teaching my friends the concepts and like verbalizing it, and like being able to properly articulate it. If you can do that, that means you understand it. So it's a great way to revise and consolidate your understanding. And also, if you like test this on a friend that doesn't actually know anything about chemistry, they can learn some fun facts, and it could be fun for them. Who knows? So work together. That's the main thing there. Another thing is use study methods that are best suited for you. So if you haven't figured it out already, what you best learn from, then probably take some time to do that, because it's best to learn that now instead of learn in the middle of your trials that you've been studying wrong your whole life. It's good to figure your study methods out now. So spend some time figuring out your study methods, and some study methods that I like to use is active recall. So if I ever had to do like definitions or anything like that, I'd use flashcards. I used flashcards to remember the word equations for all of my reactions in Module 3. So that's a form of active recall. Also blurting. So I just get like a blank piece of paper and just wrote everything I knew about a certain module. And then at the end, what I do is go in a different color pen and write down from my notes what I missed. And active recall is so much more important than note taking. You can have the most beautiful notes, but you might know none of it. You just wrote it from the slides. Like, that didn't come from in here. That came from like the computer and your teacher. So active recall is a way of knowing that it's actually in there, and you can actually fish out that information from your brain and serve it up in an exam. And then also another one that's just like general advice for anyone going to school is go to sleep. Fix your sleep schedule, because sleep is important, and there are lots of studies that you perform better when you get a good night of sleep beforehand. So if you have an exam the next day, go to sleep. Don't pull an all-nighter studying for it, because you'll probably do yourself more harm than good. Also, on the same kind of note, don't leave your studying last minute. It can be a little bit tricky, but if you leave your studying last minute, it's like less of a chance that it's going to stick. So I didn't do this until year 12, so like don't worry about this too much. But if you want to start building good habits now, it's a good idea to start building up those good habits. And that's just like at the end of the week revising what you did. It doesn't have to be like a big revising kind of thing, but just acknowledging what you learned, it can help it stick in your brain a little bit more. And the last thing is just learn from your mistakes. So as I said before, mistakes made in year 11, one less mistake made in year 12. So once you make a mistake in a paper, you can't really go back and change it once you get your marks back. So just spend time figuring out what you did wrong and how to avoid it next time. So if you do your paper and you come back finding that you don't understand galvanic cells, take some time to actually learn that and understand that, so that you won't have the same problem ever again. But otherwise, I don't have any more advice for you. So thank you for coming to the lecture. I hope you learnt something. If you didn't, sorry, I guess. But thanks for coming. Hopefully, in real time, I have actually been answering your questions, and that hopefully I answered them correctly. If you have any more questions, I guess keep on adding them in there. I think there's still time in the 2 hour block for you to answer questions. So yeah, and yeah, that's it from me. Okay, bye. Good luck for year 11 chemistry. Yeah, I have nothing else to say. Bye.